Well, hi there, everyone. Thanks so much for showing up for your math learning and starting by putting your phones away. He says, looking for meaningful eye contact. All right, so today, why am I so happy to start a new unit? I don't know. It's just like I'm actually asking. It's an open question. I'm not sure why. This is fun. I love this topic. Let's go. So, suppose we've got these two problems and we're asked to find the missing side length, but we forget how to do it. And we wanted to start by saying, I don't know, I think this x up here, x could be like certainly bigger than some number, but smaller than some other number. What number would definitely be smaller than x? Yeah, x is like clearly bigger than 3. I think we can get even a little higher than 3. That's something that's like definitely smaller. Sorry?
It's bigger than the 21.
It's even bigger than 21, I agree, yeah. Because the longest side of the triangle is going to be opposite here. So it's going to be bigger than 21, for sure. I love that. But what's it definitely smaller than? The area? Yeah. Well, it's going to be smaller than the whole perimeter of the triangle. But like if let's say I have this like 3-meter piece of string, and I stretch this end of the string as far away from this end of the 21-meter string. How long could I make this in total? If I stretched it out. 24. There ain't no way that x is longer than 24. Do people see how we built those numbers? We've got a pretty good range for this number x already. And that's pretty cool. You want to start with guesses like these because they allow you to tap into your intuition and then use your algebra. Then you get to check the results of your algebra against your intuition at the end. And when you're using both systems of your mind, both systems are speaking to one another. And that's going to help solidify the concepts. And when your calculator spits out a number like 441, you're like, that can't possibly be it. Because I had this like, it was between 21 and 24. So there's a tool. What is the name of the triangle tool that we can use to solve these types of problems?
Like if you know what kind of triangle it is, you could do different formulas. Like that's a hypotenuse.
Yeah. This one, the specific formula that we're going to use is Pythagorean theorem. So this one is even like, this is the backbone of what trigonometry is based on, is Pythagorean theorem. This is old math. These are the old ways. So Wilson, what's the Pythagorean theorem? Okay, so put your phone away, man. Okay, and oh yeah, you got something?
Yeah, a squared plus b squared equals c squared.
So we can think about this triangle as like the A side and the B side, and then the C side. Okay? C's got to be the longest one. C is the hypotenuse. Okay? If you forget which side is the hypotenuse, imagine the hippopotenuse. The hippopotenuse is the lazy hippopotamus that lays on the riverbank. Okay, so it's always like laying that way. I'm not going to draw the hippopotenuse for you. And A and B are called the legs of the triangle. The two shorter sides are called legs. They're necessarily shorter than this side, which is how we built the lower bound for x there. And we get this formula, a squared plus b squared equals c squared. There's so many beautiful proofs of this ancient mathematical fact, and I'd encourage you to watch some visualizations on YouTube. But ain't no one got time for that today. So, just like I always have you do, copy out the formula every time. This is an important communication step. You're showing your audience, because let's be clear, you don't do math to get the right answer. You do math to influence other people's behavior. I want you to build the bridge this way. Build it for me, and it should be this way. Why? How do I know this? A squared plus b squared equals c squared. Okay, I'll show you these things. So, and then we feed these numbers to our formula and evaluate. 3 squared plus 21 squared equals, this is c, x squared. Okay, so I feed all that stuff in there. I've got one equation, one unknown. I can definitely solve this. 3 squared is 9. 21 squared is 441, or at least that's what your calculator tells you, is equal to, I don't know yet, x squared. I can do that math in my head. It's 450 equals x squared. But gee golly, I didn't expect an answer like 450. Yeah?
Square root it.
Yeah, because we know we're looking for an answer that's between 21 and 24. You see how this is one way you use that guess, right? Always start with these guesses. It looks like it's about 22, I don't know. And then you check, okay? So now we square root it. Yes, we know that this is quadratic. You know, we got an x squared. So we're going to square root both sides. Do we need plus or minus here? Not really. Not really. I mean, we're not going to have a negative length. What would a negative length be? Just I measured it backwards? I turned my measuring tape around? I guess so. Okay, I don't really know what that means. All right, so I take the square root of 450, which is going to be, I'm going to guess 21.2. Okay, I'm going to guess 21.2. But again, see, start with a guess. 450, but I take its square root, and it's 21.2. Be like me. Make the guess all the time, and then your guesses get better. Okay, I didn't know that. I just guessed. Okay, so now we've got it. X equals 21.2. All right, circle it. That's our new length. And then compare it to your guess. Hooray, it works. So happy, just so happy. All right, how about this one? 10, 4, x. Give me your guesses for x.
You do 10 squared minus 4 squared.
Oh, okay. I'm going to come back to that. That's very good. That's like, you know, it's like round one, fight, and you go straight for the KO. I love it. But some people are going to more like, you know, start their combo a little slower, so we're going to step up to that. Okay, first we're going to start with a guess for x. X has got to be bigger than what number? It's got to be bigger than 4. We can do even bigger than that. Could x be 6? What problem am I pointing out if x is 6? Wilson, eyes up here. Imagine this triangle. If that x were 6. How tall would that triangle be in this dimension? Yeah, or I'm asking everyone. This is the question I kind of want you to think about. What type of triangle would it be if x were 6? It would be a straight line, folks. Can you see it? Imagine I have this side here 10, and then I've got this side here 4, some other angle, okay? And this here, if that were 6, 4 plus 6 is 10. It wouldn't be tented up at all. It would be flat. It would have to go, like if I go 4 steps this way, and then 6 steps that way, that's the only way I can do 4 and 6 and have a total distance of 10. It'd be a straight line. X has got to be bigger than 6 here. Do you see what I did to get my guess for x? Get like a good lower bound. It's got to be bigger than 6. Okay? And it's got to be shorter than, well, it's definitely going to be shorter than 10. So let's just work with that. We've already got a pretty good range there. Okay? So now let's take a look at how we set this up. We're getting there, Eli. I love how you just like go straight for it. I always do this. A squared plus b squared equals c squared. I don't know why my square went down there. And I call this a and b and c. And then I input, so x squared plus 4 squared equals 10 squared. And then I'm like, I want to isolate x. So then I go ahead and move this over, minus 4 squared from both sides. And then I get this nice line. Oh wait, isn't this what Eli said earlier? Hey, it is. But now we see where it comes from. Okay? So you can do that way, or you can have a different version of the Pythagorean theorem memorized, which would be a squared equals c squared minus b squared, and that also works for the times where you're solving for the shorter lengths. Okay? And then we go ahead and evaluate. X squared equals 100 minus 16 equals 84. x squared. And who's got a guess for me, x squared?
9.2.
That's a very good guess. I expect you're right. That's the same thing I would guess. Is it such a good guess that I don't need to check my calculator? I take this through. Oh, it's 9.16. Well, that rounds to 9.2. Okay, that's beautiful. So x equals 9.2. See how useful having that was to start. Now, hands up, those of you who can recall setting this up like this. X squared equals 4 squared plus 10 squared, because you were like, that's how this always works. And then you end up with x squared equals 116. And you take the square root and you find that x equals, that looks like about 10.8. And you're like, oh, it's 10.8. I hand that in to the teacher. I'm so proud of my work. I even remembered to do the square root. And the teacher says, that's wrong. And you're like, oh, man, I wish I got those marks. Well, set it up this way. And remember that the A and the B are the legs every time. And my main point, start with your guess so that you know about what type of answer you're expecting in these cases. So this is called Pythagorean theorem. And recently there was a pair of American students that found a new proof to the Pythagorean theorem. It was in the news. They were about your age. It was all the rage. You know, they did things mathematicians have been trying to do for a long time. So it shows you that there's still new cool things you can do in math that's not all been discovered already. Okay, what types of triangles can we use Pythagorean theorem for? Need a right angle triangle. And in fact, that's our topic for today, is right angle triangles. Good. So write this formula in the box. Get it tattooed on your wrist somewhere. A squared plus B squared equals C squared. Okay. And then if you want this rearrangement, A squared equals C squared minus B squared. This one you could say, solve for the legs. And this one you can say, solve for hypotenuse. Okay? Cool. Well, let's keep going, team. What do you know about the angles in a triangle? So let's draw a little triangle for ourselves here and label the angles A, B, and C. Okay? Angle A, angle B, and angle C plus angle B plus angle C always equals 180 degrees. Is that news to anyone? This is a little bit review, but it's one of those facts that doesn't come up a lot at the grocery store, but is super useful when we're working on triangles. If you know 2 angles in a triangle, you actually know all 3, because you just use this little formula to solve. Let's look at an example. Someone give me a number between 1 and 180.
42.
So this angle is 42, okay? Ballpark it. What does this angle look like? That was about 64. So solve for me B. So you use this little formula here. Angle A, we're going to call that 42. Plus angle B, we don't know it. We're going to say plus angle B. And then angle C plus 64 equals 180 degrees. Simplify this side. We got some like terms. 106 plus angle B equals 180. So how much is angle B in that case? Good. This one is 74. That's how that one do. Okay, so you can always use that to solve a triangle without resorting to trigonometry tricks. Okay, trigonometry tricks will also work, but it's a little bit like inventing a robot so that you can have it pull your hand apart one finger at a time instead of just doing this. It's much easier to do that than invent a robot. Okay, so that's one property of angles in a triangle. How about some names for different angles? What are some different types of angles called? There's obtuse. which are the largest types of angles that we find. They're what type of angle? But necessarily less than 180. Okay, so that's a little definition we need. Opposite of obtuse? Acute, yeah. This is between 0 and 90. Cool. We have a special name for 90 degrees. That's the right angle. Don't start an argument with a triangle with a 60-degree angle and a 30-degree angle because it will always be right. And a 180. Does anyone know what this is called? You said it. It's a straight angle. You wouldn't really think of it as an angle, but it is. It's like a straight line. It's like as we rotate and it becomes 180, it's 180. And then between 180 and 360 degrees, these are called reflex angles. Okay, so those are our names for our different angles. Very cool. If you want to see a proof for why this is always true, it's a very easy geometric proof. I can show that to you later. It's kind of beautiful. And then, what else can you tell me about the sides of a triangle? Let's recreate another triangle, ABC, and here, label it the way I label it, okay? Just like this, label this side A, this corner B, and this corner C, and then name this side little c, this side little a, and this side little b. Do you know why we have this convention of naming triangles with the, well, first of all, we use uppercase for the angles and lowercase for the side lengths. But do you know why we have these pairs that are opposite one another in the triangle?
So you can use cosine law?
It does connect to cosine law and sine law, yeah. Yeah, it does. And there's an intuitive reason for why that is. Imagine I take a laser pointer, okay, and I'm going to shine my laser pointer up the wall, and I'm going to change the angle here. Call this my angle of interest, or A, okay? And then I measure how much it moves up the wall. As I change A, it changes that side length most directly. It doesn't change this side length of the triangle hardly at all, and it changes the hypotenuse a little bit. But the hypotenuse changing is a function of that one changing, and that one is directly related, as I change the laser pointer there, to this angle. So you have these like opposite angles. You can imagine as I open angle A, side A will grow. Okay? So there's that. And then, like we were looking at before, if you have, is this triangle, let's say I'm going to create a triangle here. This side length is 100, this side length is 50, and this side length is 2. Is that triangle possible in the dimensions we inhabit? Why not? Hold your arms out straight to the side. Try not to poke your neighbor in the eye. And then without bending your shoulders or elbows, only your wrists touch your nose. It's impossible, right? I need to bend at my elbows. I need these to be longer, right? These legs have to be longer. So what you have here is impossible because this plus that is less than this, and that's impossible. So here is an equality we always have. B, which would be one of the sides of the triangle, is always less than A plus C. A plus C always has to be greater than the other side. And that's true for any side in the triangle. Any side on its own has to be less than the sum of the other two sides. Okay? We can also rearrange that and say B minus C is always less than A. Okay? Any one side of the triangle has to be greater than the difference of the other two sides. If it's not, then your triangle's not a triangle. It might be a trying to touch my nose in this weird way type of situation. Okay? So we've looked at types of triangles. There are acute triangles, obtuse triangles, and right triangles. So those are based on the angles that are in there. And an acute triangle will have 3 angles that are all less than 90. A right triangle has exactly one that's 90. And you'll also find if you have 2 angles that are 90, that that's not a triangle as well. And then an obtuse triangle has exactly one angle that's between 90 and 180. Okay? But there are 3 other types of triangles that we'll talk about this unit. What are the other 3 types of triangles? I'll draw them. Oh, it's so beautiful. It's so mathematically perfect. And this is 60 degrees. This is 60 degrees. And that's 60 degrees. What type of triangle is that? That's equilateral. If you remember the word equals, then this one is pretty easy to remember. All the sides are the same, all the angles are the same. Okay? How about this one? Looks like a party hat. This one is isosceles, and those 2 angles, we don't know what they are, but we know they're the same. Okay, those 2 corner angles are, oh no. I think I spelt it right, but I really struggle with this word. So if I spelled it wrong, I don't know if I'm going to count it as an error. I know I would check, but I'm not going to. And then there's a 3rd type of triangle. Most right angle triangles are this type of triangle where all these sides are different. This one is called a scalene triangle. Most triangles are scalene. Okay. All right, before we keep going, I know that there's a little voice in your head. A little voice in your head sounds like this. Oh man, more math facts. This time a whole unit about triangles. I don't know why I should care. Help Cozy Cat understand why triangles are so important, and we're going to spend a lot of time on them. What types of problems do they help us solve? Where do they show up? Who uses them in their job? Construction, architects, okay? What's particularly important about a triangle for like building structures? They're extremely strong, yeah. So, and you can imagine that like you built it out of squares, a square can crush over, become a rhombus, and then become a straight line. But an equilateral triangle is your geometrically most strong shape. So a series of triangles is much more effective than a series of squares. So that's one place they show up. So if you're building something or being an architect, particularly an architect wants to make sure that they know how long the different sides are and that it is indeed a true triangle and that it works in the context of what they're building. So there you go. Construction, architecture, those are one place where you're going to see it. And that's one place. Phones out, people, I see you. So what? So where else? Other ideas where we see triangles? We're going to see it all over in engineering, right? We're going to see it in where is that thing in space? It's over to the left this much and up to the up high that much. So how far of a wrench do I need to reach there or something like that? Yeah, it's all triangles in engineering and building and those types of things. Computer graphics are going to use a lot of locate the point this way, that way, find out where it is, find out how far it is to that upper window so I know if the Call of Duty weapon will have the range to reach there. It's all trigonometry in computer games. Are triangles complicated shapes or simple shapes? They are the simplest three-dimensional shape. And many other shapes can be deconstructed to triangles. Triangles are highly analyzable. And that's where, because we have these tools to analyze triangles, we can analyze more complex situations by dissecting them into triangles. So how about just geometry generally is another thing. Surveyors will use triangles to measure objects that are too distant to measure directly. We can use triangles in trigonometry to do that. Finding points on a map, coordinate points, triangles. They're everywhere, folks. So we want to satisfy Cozy Cat and make sure Cozy Cat knows the work we're doing, it shows up. It's important to math, it's important to tech. It's important to surveying, to knowing where to find things. Triangles. You want to think about cell phones and triangulating the killer based on which cell phone tower they were using and how far away they were when they made that call about where they put the body. Stop putting these ideas in my head, Cozy Cat. Okay. Now, this is, again, not new. It's review from grade 10. Both academic and applied had these SOHCAHTOA skills, but this is like the most recent. This is the freshest cut. The last ones were real deep cuts, okay? So now we want to think about, hey, I don't have two sides. If I have two sides, and I want the third side, then I use Pythagoras. If I have one side and one angle, then I use sine, cosine, tangent. Related by your SOHCAHTOA, if you remember that. If you want more earworms, I can play you some SOHCAHTOA songs. Prove to me that you don't need it. Show me that you can remember your SOHCAHTOA. Okay, so here are the steps for solving. There's an important step I want you to write on. It's that important, and it's not emphasized by other math teachers. That's why it doesn't show up on their handout here. But the step, this is like step 0. Start, how do I want you to start? Start with a guess. And then after you solve 4, check your guess. That way you start with intuition, go to algebra, and then go back to intuition. And then your intuition builds your algebra, builds your intuition. And you find more errors. So, and then correct your errors. That's the idea. So here we go. This is a 35-degree angle. That actually looks fairly accurate. That actually kind of looks, if I had a protractor, closer to 30 than 35. But I think the diagram is pretty good there. If this side is 20 meters, about what would you guess for that side that we're interested in? Would you think it's like 5 meters, 15 meters? Give yourself a minimum and a maximum. Where do you think your guess is going to be in between, your value is going to fall in between? Charlie, what would be a number so small you'd be mildly surprised if it came out here?
Maybe like 4.
Yeah, 4 would be pretty surprising. It would be pretty short. And so we got 4 as our lower bound. So 4 is going to be less than h. And Chase, can I use 15 as the upper one? Sure. So 15, if it came out 15, I'd be pretty surprised that it was that long. My guess is going to be 11. My guess is 11. So, how do we do this? Well, we're going to label the sides of the triangle OHA with reference to the angle of interest. The angle of interest is this angle down here in the corner. We're interested in that angle. We're measuring from that angle. So this side over here is what side? Opposite, hypotenuse, or adjacent? This is the opposite side. This is the hypotenuse, and this is the adjacent. I know that one is opposite because it's opposite the triangle from the angle of interest. I have to go all the way across the triangle. Adjacent means right next door, like Brielle is adjacent to Lorraine. Do you take notes on your phone or something? What do you do with your phone? So here, so there you go. We've got opposite, hypotenuse, and adjacent. Now, we want to determine which ratio we're going to use. Which of these ratios, sine, cosine, or tangent, is interested in the adjacent and the opposite? Sine is opposite and hypotenuse. Cosine is adjacent and hypotenuse. Tangent is opposite and adjacent. Okay, so that's what we're going to use. So here's how we set it up. Solve. We're going to explode this one and figure it out. So you can start by writing down your formula. Okay, let's go. So tangent of some angle, okay, is equal to opposite divided by adjacent. Write down your formulas every time, and you will get better at math. And you will make fewer errors. And you will get the opposite in the right place and the adjacent in the right place, and you won't flip them with some weird wishful thinking. Okay, and next, write down your unknowns. This is our angle of interest. This is our opposite, and this is our adjacent. So put those things there. Tan 35 degrees is equal to h, which is the height of this triangle. Very interesting. Over top of 20. And now it says, we'll solve. How do we solve something like that? Tan 35 equals h on 20. I want to isolate h. I want h all by itself. But gosh darn it, h is being divided by 20. I sure wish it was just h equals. How can we make Cozy Cat happy here? Eli? Yeah, we do the opposite of divide, which is multiply. So multiply both sides by 20, and that will give you the thing you punch in your calculator. Multiply by 20, multiply by 20. So now this cancels this, and we've successfully isolated h, and this is the thing we go ahead and proudly punch in our calculator. 20 multiplied by, I type it in first, 35, but I take the tangent of it. So tangent 35 is 0.7. Oh, we're going to be bigger. So we are going to be 14. Wow, that's amazing. Oh, of course, I see why my guess is so bad. Yeah, okay, and see, I check it against my guess, and then I refine my guess. My algebra here is correct, and it helps me guess better in the future. Okay, so we got 14.00415, so round appropriately. We could say in this case 14.0 equals h. Why did I add an extra decimal place if it didn't change the number? And I write in here meters because I keep my units. What's the difference between saying it's 14 meters tall and it's 14.0 meters tall? How's that different?
14.0 is more accurate because you know it's exactly 14 and not 14 point whatever.
Right. So it's a communication question. I'm communicating to the person reading this that it's 14 and very close. It's accurate to the tenth. So it's definitely 14.0 meters. Good. And then check against our guess. It falls in this range, so we're pretty happy. And we know that we didn't make some weird error along the way. Let's keep going. We got 15 centimeters there, and we want to solve for this h. So start with a guess. We got 31 degrees. Again, that looks about right. About how long do you think h is going to be here? Someone give me a lower bound and upper bound. Brielle, put your phone away. What? Why is it so exasperating? It's like the gentlest of hints, the leading up to me pointing this out. Put it away, man. What are we looking here for h? Give me some guesses. Oh, and what number would be so small that you would be surprised it pops out of our algebra? 2. If this was 2, we would be pretty surprised. But what number is it definitely going to be quite a bit deal smaller than? Yeah, it's got to be less than 15. So as you guess, you can get these numbers in a little tighter. My guess here is going to be 7.501. 7.508. 7.508. Okay, let's see. So now, label your sides. We got hypotenuse. We've got our angle of interest over there. This is again the opposite, and this is the adjacent. We're not interested in the adjacent side, but we could find it next, either with cosine or with, what's it called, Pythagorean theorem. Which ratio is going to relate the hypotenuse to the opposite? Oh, right, there it is, opposite and hypotenuse. So katoa. Okay, so we're going to say sine of some angle is equal to the opposite over the hypotenuse. Your hand will not fall off if you write this every time. And then we substitute in. Race me. See if you can finish this faster on your calculator than it takes me. Oh, we're dividing hypotenuse by 15. I remember that the opposite of divide by 15 is multiply. And then that's what we go ahead and proudly punch in our calculator. 15 multiplied by 31.
7.72.
7.72. It's not 7.5. That 1 degree made a lot more difference than I thought it would. Cool. All right. Good. H equals 7.7255. So we could say 7.73 centimeters. And now we've got it accurate to 1/10 of a millimeter. We check it against our guess. It's well inside the bounds that we set for our guess. So we're pretty happy. And later on, we refine our guessing to get a little closer, a little closer. Okay. How about this one? If this side was 9.7 centimeters, ignore this M there, I don't know why it's there, and we want X, the hypotenuse, what number would you expect X to be definitely bigger than? It's definitely bigger than 9.7. You care to have a more risky guess that's a little closer to X? Yeah, it's going to be bigger than 10. Okay, good. That is indeed closer than 9.7. And what number would be so big you would be super shocked if it came out here? 101. Okay, 101 would be absolutely shocking. Start with a little guess. X is somewhere in between 10 and 101. Sorry? Okay, you got it now. So how do we solve this one? Yeah?
Would it have to be less than 20 or no? No.
Less than 20? I think it's going to be a little bigger than 20, to be honest. My guess would be, let's say 22 is what I'm guessing. Yeah, that's where I'm going to put my guess. Because I happen to know that if this was 60, this would be double.
I just thought, yeah, sorry, I thought the one that was almost 10 was taller than it is.
Okay, cool. So that's almost 10. Yeah, there. So, yeah, but, yeah. So now, here's our angle of interest. So let's label our sides. Which one is the hypotenuse? Which one is the opposite? Which one's the adjacent?
X is the hypotenuse.
This is hypotenuse.
Adjacent is the one that just the line that's the top of the screen.
This one here is the adjacent?
Yeah. No, opposite. That's opposite.
Oh, okay. That's the opposite. Good. Yeah. This one's the opposite because it's across the triangle from our angle. And now we're interested in adjacent and hypotenuse together. So how do we solve these situations where we have adjacent and hypotenuse? Yeah. Which trigonometric ratio relates the adjacent to the hypotenuse?
Cosine.
Cosine. So we're going to use cosine here. Write it down every time. Cosine of theta, which is just some random angle, is equal to the adjacent divided by the hypotenuse. Good. Put in your unknowns and your knowns. Cosine of 63 is equal to, the adjacent is 9.7, and the hypotenuse is x. How do I solve this one for x?
9.7 times cos 63.
So right now, x is dividing 9.7. I've got x downstairs, and that's hard. So what can I do? It's hard when your variable's in the denominator.
You divide by cos 63 instead.
If we divide both sides by cos 63,
No, divide 9.7 by cos 63.
well, that's correct. But you're a little bit like Eli going for the killing combo right away. So, I mean, you're absolutely correct. But let me show you what we do. It's annoying that x is in the denominator, so multiply by x, both sides. Now this x cancels that x, and we get this line. X times cosine 63 is equal to 9.7. And now, gosh, wouldn't it be easy if x wasn't being multiplied by cos 63?
Yeah.
So, Charlie, what do you want me to do now?
Put 9.7 divided
Yeah.
Both sides, yeah.
Sure. So this cos 63 cancels that cos 63 because it's just a number. And then it pops out over there, 9.7 over cos 63. X equals 9.7 over cos 63. Let's just punch it. 9.7 divided by 63, but I take its cosine. 21.3. Cool. What did I say, 22? I guess pretty good, not great. So x equals 21.3, and we're pretty satisfied with that. Oh my goodness. A wheelchair ramp is required to have an angle of elevation that's not greater than 8%, 8 degrees. If we have to reach an entranceway 4 feet off the ground, what horizontal length do we need this wheelchair ramp to have? Set up a diagram. Word problem. Oh, I see I need to make a diagram. I'm going to draw my entryway here. Okay. And it's up there. 4 feet. I've seen ramps in the past. Oh, look, a ramp makes a triangle. And because we're comparing horizontal to height, we have a right angle. So we know that the right angle goes there. This is 8 degrees, and we want to know the horizontal distance x. So now that I have this triangle, what will relate these two? Which trigonometric ratio? Label them first. Which one's opposite, adjacent, hypotenuse? Sine and cosine are like buddies. They're very similar to one another. Oh my goodness, why is it like so tricky to just put it in your bag and keep it away? So sine and cosine are like buddies. They are related to one another because they both involve hypotenuse. Tangent doesn't involve hypotenuse. Tangent is like the strange cousin that you only see like twice a year. Which one here doesn't involve hypotenuse? The tangent. So we go tangent of some angle is equal to SOHCAHTOA. Oh, right, opposite over adjacent. So we get tan 8 degrees equals opposite is 4. That's opposite the triangle over x. Rearrange here. X equals, as Charlie says, 4 divided by tan 8. And I say that's Charlie's move because Charlie does this in one line, which is pretty cool. Multiply both sides by x and divide both sides by tan 8 to isolate x upstairs on the other side of the equation. Same as what we just did. These cancel. You get 4 divided by tan 8. You proudly punch that in your calculator. But you guess first. About how long do you think we need to go up 4 meters at an incline of 8 degrees? Sorry?
3.85.
3.85? I think we need a lot longer run than that. Yeah, I think we need a lot longer run than 3.85. I think we got to go for meters and meters and meters. This is a long ramp. We might need like switchbacks on this ramp to get up to that spot. But you would just line up your switchbacks and it would be the same length overall if you wanted to keep it at 8 degrees and just do it in parts, right? People have seen switchbacks like that. So let's look at it. 4 divided by 8, but I take its tangent, equals 28.5. So we need 28.5 meters. Sorry, 28.5 feet. Yeah, we're not going up 4 meters. That's like going up a story. No,
Yeah.
4 feet is like a part of a wall. Yeah. Yeah, so we need about a little less than 10 meters, or 28.5 feet. Cool. And then, this was given to us in a sentence, so answer it in a sentence. Here. Ba-doop, boop, boop, boop. Practice. Yeah. For you, anything.